Hello grade 11s, my name is Clinton van der Merwe, and today we're going to look at lesson 3 in your climatology section of the syllabus, which is entitled or all about Africa's climatic regions or zones. Now remember, everything we've done in lesson 1 and lesson 2 builds on as the foundation of what we're going to discuss in lesson 3 and eventually then in lesson 4 later as well. So all that you've learnt about with the global circulation, pressure, and the relationship of temperature and pressure to wind is going to be significant for understanding this section, which looks at Africa's climate, or on a more regional scale, what's going on with the continent of Africa weather-wise. Right, so if we have a look at your first slide there, we are looking at Africa's climate regions, or climatic regions, as they call it in some textbooks. Remember, a region is an area or a place where the climate is quite similar or the same. And remember, when we talk about climate, we mean the long-term average weather conditions that a place experiences or that characterizes an area. Some of the key concepts we're going to be covering here when we're looking at this section of Africa's climatic regions or zones. First of all, you must know or be able to do the following things: name and understand the various characteristics or special facts about the position of Africa's major climatic regions or zones. Secondly, we're going to be able to try and look at the link between the African continent circulation, how air moves in relation to the global or the Tri-Cellular arrangement, which we looked at last time, and how that affects areas where there's uplift of air, which means you get rainfall, or where there's subsidence or sinking motions of air, where we get no rain or dry conditions prevailing. To identify the major ocean currents around Africa and the influence on the climate control over Africa is very important. We have to know if it's hot or cold water and what's that doing in relation to the air above it. And then we're going to try and look at a very complicated concept here, which a lot of the science and scientists in the world are still grappling with, and that is to try and fully understand the processes involved in what we call El Nino and La Nina, and the effects that this has on the African climate as a region. Finally, being able to interpret synoptic charts, we're going to be using weather maps of South Africa with special reference to air movements and interpreting of station models to understand weather, as well as looking at our dominant pattern of high pressure cells or our anticyclones, which are affecting our climate. Now remember, a lot of what we're going to be doing is going to be recapping stuff you would have learned in grade 10. So everything you've learned in grade 10 in climate builds on and gives you the foundation for what we need to cover in grade 11. Right, so then if we move forward now, let's start our first section, which is the characteristics and position of Africa's major climatic regions or climate zones. Africa's position is very important. Where we are in the world is relatively unique in the sense that it is almost a mirror image of the climate zones which occur both to the north and to the south of the equator. In terms of that latitudinal effect, we have 6 main climatic zones of Africa which are found north and south of the equator, namely the Equatorial zone, then the Humid or Tropical zone. Plainly, the third one would be the Tropical zone. Then we talk about something known as the semi-desert or Sahalian region, and sometimes they spell that in textbooks with an E over here, so don't get confused. It's not a different word, it's the same idea or concept. And then we're also going to look at something called the Mediterranean climatic zone, which is like Cape Town, and finally the desert. Deserts of the world make up large portions of Africa as a continent. Here's the definition of what we mean by a climate zone. A climate region or a climate zone is an area with similar temperature and rainfall patterns. They have the same temperature dynamics and the same rainfall sort of measurements over that sort of spatial area. In grade 10, you learnt about several factors that influence the climate of different places in the world, and these were latitudinal position, altitude, distance from the sea, prevalent pressure belts, and ocean currents. Now remember, if you don't know all of that, you need to go and do a little bit of revision or recapping before you can understand a few of the concepts and ideas that I'm going to explain today. Right, the first thing, when we're talking about characteristics and the position of Africa's major climatic zones, Africa is made up of these 5 different zones or climates. And here is a map of Africa, which is color-coded very nicely there for us. You can see all those different shades of colors represent the 5 distinct or different zones that we're talking about. Okay, and more or less, remember the equator runs through over here, which separates us into the northern and the southern hemisphere as a continent. And so you can see what I was saying earlier, that the northern and the southern parts of Africa relative to the equator are basically mirror images of one another. Now what's important from this map is here you can see, if I just point out some of these things over here with a little circle again, the green zone is basically the equatorial zone. There you can see around the equator, just north of the equator and a little bit to the south of the equator. That's what we call the equatorial climate zone. But then we also have smaller circle here to make it easier for us to see now, the humid tropical areas, right, where it's very humid but still tropical. Then tropical is that green pale color. Then we have the Sahalian regions, those gray areas, which is semi-desert or very dry and arid. And then the desert regions, or where it's very dry and very hot, you can see depicted there by this yellowish color over there. Then the Mediterranean regions, where it's often raining in winter, and we call it Mediterranean because it's got that sort of characteristic winter rainfall like in Europe, or the Mediterranean Sea, is just this little zone up here on the top northern part of Africa, and then this big section down here, which is southwestern and eastern sort of Cape region, where we have a Mediterranean climate in South Africa. Also, the other things that are significant over here, which I'm pointing out now, is the different ocean currents. Here on the northern section of the bulge, we've got the cold Canary current. Remember, this is cold water coming from the North Pole. Down here, we've got our famous little West Coast current, which makes it so freezing to go and swim in the Western Cape. You have to wear a wetsuit if you're going to get in the water there. That's known as the cold Benguela current, and that's also cold water because it's coming from the South Pole. Then we've got some warm ocean currents. Remember our discussion in last lesson. Mostly eastern continents have warmer water because here the water is originating from the equator. So we've got, first of all, for South Africa, what is known as the cooler but still warmish water Agulhas current. Further north, it's known as the warm Mozambican current, which goes through between subcontinent of Africa, and this is Madagascar over here. And then finally, the Somali is a warm ocean current which goes up along the Somalian coast over here from the equator again, warm water, and that has a moderating impact on the climate. Ocean currents, remember, help to moderate our temperatures of air. Right, so there's the map of Africa, and just underneath there in your notes, you'll see I've characterized very briefly, we'll just do 1 or 2 examples. The desert region runs between 18 and 36 degrees north and south of the equator. It is what we call the subtropical high pressure zone. The west coast and continental effect is quite characteristic of this type of climatic region, and the reasons are because of that cold Canary ocean current and the cold Benguela current. Equatorially speaking, remember we've got, relative to the equator, a zone further north and south of the equator by about 10 degrees, where the ITCZ, Intertropical Convergence Zone, sits, and this is affected mainly by the continentality of the west coast and also that current that flows up along the west coast of Africa. The humid tropical climate region is your transition zone between equatorial and tropical or savanna areas of the world, particularly in Africa, where you get rainfall throughout the year, but there's much more rain in summer usually. Small variations in temperature, this should be the degree symbol over there. 20 to 25 degrees Celsius is the temperature range, and the high temperatures in this region is because of its tropical location being at the Tropic of Capricorn and Cancer relative to the equator, north and south. The Sahalian or semi-desert region, that grey area that we spoke about, is 20 degrees north of the equator, and this is a transition between monsoonal and desert zone conditions. Right, this is not repeated in the southern hemisphere. It's predominantly a northern African phenomenon, but the ITCZ is what's moving north to create summer rainfall, although this area of the world is mainly continental with its climatic characteristics. Remember, we spoke about the continentality or the maritime effect of climates, that land heats up faster, cools down quicker, water heats up slower but retains its energy for longer. So the specific heat capacity of land and water, or the maritime versus continental effect of heating or temperature, has a significant impact on climate. That blue zone, what we call the Mediterranean region, 30 to 40 degrees north of and south of the equator, this is where you are situated on the furthest northern and southern west margins of the African continent, and you have a lot of winter rainfall happening there as a result of temperate cyclones or mid-latitude cyclones, which you'll learn more about in grade 12. Very maritime climate related to the sea and the moderating effect of oceans. And the final zone or region there is the tropical or savanna climate region, 15 to 20 degrees north and south of the equator, where your subtropical high-pressure belts or your anticyclones are strongly influencing the climatic experiences, particularly in winter. Summer rainfall, this is a region prone to droughts and tornadoes, and this is where you have large ranges in temperature between day and night, as well as season to season. Then your subsidence and convergence in Africa is a very important concept to just put into your minds and to get clearly understood in your own thinking. If you have a look at this diagram here, Africa sits predominantly between 37 degrees north of the equator. Here's the equator, which is 0 degrees north-south, and then 34 degrees south, the southernmost tip of South Africa, there by Cape Agulhas. That's the latitudinal extent or positionality of where we sit in the world. This is also known as the ITCZ, the Intertropical Convergence Zone. Some textbooks, they talk about the heat or the thermal equator. And this is significant because we'll look at how your trade winds converging here in the intertropical areas create that low pressure belt that dominates or sits in the middle of the world, as it were, and moves from season to season because of the tilt of the Earth on its own axis. So you can see in this diagram, to the north and south of the equator line there, we have our Hadley cell that we spoke about last week, or the last lesson rather, lesson number 1 and 2, where we were dealing with the global circulation of air patterns because of pressure and moving air, which is wind. Right, so Africa straddles the equator. We have 2 subtropical pressure belts that we need to speak about or remember. Remember, those are the ones that sit here, the subtropical high pressure belt of the northern hemisphere, and then here in South Africa, where we know that we've got those high pressures that sit at this region of the Earth, known as the subtropical high pressure belt of the southern hemisphere, and we've spoken briefly about those as your South Atlantic Kalahari and South Indian anticyclones that sit at those latitudes. Between the 2 pressure belts, we have this ITCZ, also known as the heat or the thermal equator, like I said, and that is what moves north and south of the real equator from season to season because of the tilt of the Earth on its own axis. It is responsible, or this is the area of massive uplift over Africa, and very high rainfall patterns or figures are measured over here. You can see there from that diagram, we've indicated the cumulonimbus clouds and the thunderstorms or the lightning there. That means we get rain along the equator just about every day. The subtropical high pressure belt also migrates seasonally with this movement of the overhead sun. Remember, we spoke about that very briefly in the last lesson. Areas in Africa have their rainfall season when the heat equator moves into its respective hemisphere. So when the ITCZ is sitting south of the real equator, then we know it's summer for the southern hemisphere. And remember, when the intertropical convergence zone sits to the north of the real equator, then we know it is our winter and the northern hemisphere's summer. Remember the solstices we spoke about in the last lesson as well, where it is your longest day and your shortest night. Figure 2 is more simplified. It shows conditions for an equinox with the overhead sun happening over the equator. And remember, this was figure 2 that we were looking at over here. So if this is an autumn or a spring scenario, this is how things would relatively be sitting. The pressure belts would be in their positions during those months of the year where we're starting to warm up or starting to cool down, depending on what hemisphere you are in, autumn or spring. Right, the role of oceans is very important in the control of climate in Africa. The ocean covers, remember, as we saw previously, more than 3/4 or 70% of the Earth's surface. They play a large or major role in regulating, moderating the weather and the climate conditions on the planet. Oceans in general have a great influence on rainfall, particularly, and on a continental basis, and they also influence the temperature of your air along the coastal margins or regions of your continent. In figure 3, we see there's an isotherm map that shows ocean temperatures around Africa. If the ocean currents are superimposed onto this map, there will be a striking correlation between the cold ocean areas and your colder waters, and the warm ocean areas and your warmer waters. And remember, water has an effect of also warming up the air it comes into contact with. Through the process of conduction, you've got air being warmed up by touching something that's cold or touching something that's warm. The temperature of the air starts to change through conduction. Here's a very good definition of what we mean by an isotherm. An isotherm is a line on a map joining places that have the same temperatures. And here you can see the average sea surface temperature of Africa is depicted using various shades, from red, very hot, down to purple, very cold, -3 degrees on your scale over here. Remember, we use the scale of the axis to look at the temperature in degrees Celsius, and there you can see all the warmer water sits here in the equatorial to tropical regions, both north and south of the equator. And then as you go north, it gets colder, and as you go south, it gets colder towards Antarctica or the North Pole in the northern hemisphere. And there you can just see how we've circled 2 little things there showing you the temperature ranges for how they're the same, in fact, at the same latitudes. Here, 30 degrees south, you can see the temperature ranges between 17 and 21 degrees for the water. And there, the sea surface temperature is about the same, 17 to 21 degrees as well, at these latitudes, 30 to 40 degrees north of the equator in that region as well. Remember, by average sea surface temperature, when we're talking about the concept of sea surface temperature, we are talking about the first layer of 1 meter to 3 meters of water, the surface layer of the sea that has got a particular characteristic of temperature being recorded there. Right, if we move along, we're still looking at the role of oceans in climate control for Africa. And temperature-wise, if we look at temperature as our first variable or our first major component, the effect of ocean with regard to temperature is maritime in effect. In other words, the seas control the temperatures along the coastline, moderating them. Generally, when looking at temperature of the oceans and currents around the coast of Africa, there is a dominance of warm water around the continent. The exceptions are the northwest and the southwest coastlines, which I was pointing out in that previous diagram that we looked at earlier, where your cold Canary current and the cold Benguela ocean currents, respectively, are moderating the temperatures down rather than up. If we quickly go back to that diagram, this is what we were meaning over there when I was showing you that and that over there. That's what we're talking about in this bullet on the next page here in your notes. All right, the Mediterranean areas are always cooler or colder than expected due to the cloud cover that happens there in winter when it rains so much more. And as the cold fronts also associated with your temperate cyclones or mid-latitude cyclones move through and lessen the insolation that occurs in these regions of the world, we have a Mediterranean climate that you can see in 3 and 4. There it is circled again, those regions, Mediterranean regions over here and there. Since South Africa is surrounded by water masses, all coastline temperatures are moderated. In other words, warmed up or cooled down significantly, and have small temperature ranges. If we look at this world map over here, this is a summary of the basic ocean currents we spoke about last time. You can see here is South Africa in the world, and we are almost surrounded by water on all sides there. Coming down from the equator on the east coast, or what's the Indian Ocean, we have the warm Agulhas and becoming Mozambican current, which raises temperatures of the eastern coastline. And then the cold Antarctic water, which is part of this Atlantic Ocean to the west of South Africa on the west coast, our cold Benguela current over here, is what diminishes or reduces the temperatures along the west coast of South Africa quite significantly as well. Staying with the role of oceans in climatic control in Africa, but moving now on to a second factor or reason, when we look at rainfall, the map of average rainfall over Africa, right, average rainfall, how much rain they get throughout the year, annually shows a similarity to the maps that show climatic regions, which I introduced you to a little bit earlier. The effect of ocean temperatures and currents has a maritime and a continental effect, depending on where you are. This, together with the migration of the heat equator, or remember what we call the thermal equator, which moves relative to the real equator from season to season, presents a rainfall pattern of considerably more rainfall over sub-Saharan Africa. Remember, the movement of the intertropical convergence zone is quite significant for your pressure belts moving from their positions when you have the equinox or autumn-spring to where you have your solstice or summer-winter. And that northwards or southwards shift of the thermal or the heat equator not only affects your pressure belts but also influences your rainfall regions or patterns significantly when that shifts seasonally as well. Here is a map of Africa which shows you, this is figure 5, the average annual precipitation for Africa. Right, you can see there the outline of Africa and the various shades of blue that are depicted on this map. And what we've done is we've enlarged the scale of the rainfall, which we measure in millimeters, remember, using a rain gauge. We've enlarged that here to the right as a big block. So all these dark blue areas where you are seeing this sort of region over here, or this sort of zone over here, that is where we're getting more than 3,000 millimeters of rain in a year. Can you see that the further north you go and the further south you go, the rainfall significantly diminishes latitudinally, so that here in South Africa, this region of the sort of northern Cape, where they've got this blue color over here, 3,000 or less than 3,000, 2 to 3,000 millimeters of rain. And then these white zones of northern Africa over countries like Algeria, Libya, and Egypt over here, we're talking about between only 100 and 300 millimeters of rain in a year. So this map shows you the average rainfall for Africa throughout the year. So processes of El Nino and La Nina. This is now that complicated concept we spoke about, and we're going to look at how it affects African climatic regions. Now, La Nina and El Nino are Spanish words which are related to December time, or when there's usually Christmas, and we associate that with the birth of Jesus. So these things are round about December, Christmas time where they become noticeable or obvious, and that is why scientists have given them this name. It's quite a regional phenomenon, but it has global influences or global impacts on our weather patterns, rainfall particularly, as well as temperature, which can lead to things like droughts or desert-like conditions. Now, if we have a look at your notes here, the effect of La Nina or El Nino, as it's called, these are two different things. La Nina is what scientists think of as being the usual or the normal climatic conditions, and then El Nino is the converse or the opposite of that, where things seem to go haywire for some reason. So the effects of these two, La Nina and El Nino, are part of what is called the Southern Oscillation, the movement of your Hadley cell as it moves throughout the year, and then seasonally things seem to change or go wrong. In Africa, there are two main areas affected, where dry areas receive more rainfall, so all of a sudden places get more rainfall that they're accustomed to, while wet areas where you are normally familiar with the rain get less average rainfall, and they can go into places or conditions where you start having drought conditions being experienced. Now, the Southern Oscillation, you'll read this in some of the textbooks, originates over the Pacific Ocean, the largest ocean of the world. We'll show you that on a map in a minute. This changes the normal pressure patterns over the entire surface of the Earth. Now, we spoke about the pressure belts in the previous lesson. Remember, we've got a low pressure belt at the equator, high pressure belt at the subtropics, and then the further north you go and the further south you go, you eventually encounter a middle latitudinal low pressure belt area, and then obviously the north and the south poles are high pressure zones or areas. With changing pressure, winds are affected. Remember, there's that relationship between pressure and wind. Air moves from a high to a low pressure, and obviously we spoke about those various cells last lesson, with the Hadley cell, the Ferrel cell, and the polar cell, and each of those have got predominant surface winds. Tropical easterlies or northeast, southeast trades, depending which hemisphere you're in, for the Hadley cell, your westerly wind belts in your Ferrel cell, and then your polar easterlies, which blow in the polar cells north and south of the Earth. All right, this diagram shows us the normal as well as the abnormal weather conditions that we associate with La Nina and El Nino specifically. This is a diagram which has two maps on it. If we look at the first map first, what is entitled the normal or the La Nina, scientists think that this is the normal scenario of what weather should be doing and looking like. We are particularly interested here in this latitudinal extent of the world, which is known as the Hadley cell. 0 to 30, 35 degrees north, 0 to 30, 35 degrees south of the equator. And just to contextualize what's going on in this map over here for you, here is Africa, here is South America, here is Australia and the Far East, Manila, Philippines, all of those places over here. So this is the largest ocean in the world, the Pacific Ocean, that separates these two continents over here. Now, normally speaking, remember we've got a high pressure normal belt up here, the subtropical high pressure or the Tropic of Cancer, high pressure area over there. And winds would normally blow from a high to a low like that, which would be your southeast trades and your northeast trades, depending on what hemisphere you are in. Now, in the southern hemisphere, these winds that are blowing here, your southeast trade winds, which is written over there, they blow the surface of the water, which I'm circling over here, in that direction, and the warm water then is moved across to that side of the world, and we have an upwelling over here along the Peruvian coastline. And in some of the textbooks you'll read about this upwelling of nutrient-rich cold water, and that's what makes the rich fishing industry so popular along this western coastline of South America. That's the normal scenario where things are normal and happening. If we look at the rest of the world over here and how it affects Africa particularly, because that's what we're trying to do, we have wet and cool conditions here in that thin circle. Things are wet and cool and as normal. And here with that blue circle, things are a little bit drier and also hotter in terms of temperature. This is the La Nina scenario where the Walker circulation, you might read that in the textbook, of what's going on over here is doing what it should be doing. But then scientists are not entirely sure why we have El Nino. We just know what it is and what it does. But the why or the reason is the big debate in the whole issue. For some reason, it's related to a change in sea surface temperatures, and we don't know what causes that necessarily, but winds are negatively affected, and winds weaken or even reverse to a certain extent when we have El Nino, right, with that little accentuation written on the N over there. Now, in El Nino, around about December time, where the weather seems to go topsy-turvy or turn itself upside down and goes all haywire and weird, for some reason here, that zone where we saw previously was dry and hot, all of a sudden goes to wet and cool conditions for a number of years at a time. And this thing happens in a cyclical fashion. Sometimes it lasts between 7 to 10 years, and it seems to happen every 7 to 10 years as a process as well. We'll look at a graph in a minute which is going to demonstrate the rainfall changes like that. Then this area down here, which in the previous diagram you saw was wet and cool there for Africa, and that area around Mauritius becomes dry and hot for all sorts of reasons, and this is related to El Nino. Now, you'll see the high pressure area here, which is normal, and then this low pressure area, which becomes high pressure, is now abnormal. And for all intents and purposes, the whole thing shifts here to the middle of the Pacific Ocean, and instead of it raining over Australia, Manila, and those places over there, we have the rain falling over here in the middle of the sea. And these places go into hot, dry, droughty conditions, whereas this poor upwelling here doesn't happen as effectively, and Peru goes into a little bit of an economic decline where their fisheries industry falls apart for a couple of years at a time. So these southeast trade winds are weakening for some reason, and the upwelling doesn't occur, and all the pressure belts are shifted out of their normal positions or localities, and things go haywire and El Nino sets in. El Nino basically changes the weather conditions, and what used to be hot and dry, the temperatures change and it becomes wetter, and they get a lot of rain all of a sudden. And places that were traditionally sort of well watered and received good levels amount of rainfall all of a sudden go into hotter, drier conditions, and they can even experience droughts as a result of El Nino. And El Nino has even had an impact on South Africa. If you look back at the historical records of our climate data, often our droughts are associated with an El Nino event, and we have less than normal rainfall or drought conditions occurring. If we have a look at our next slide over here, the processes of El Nino or La Nina as it's known over there, and the effects that it has on the African climate is as follows. The effects of the Southern Oscillation, this movement from La Nina to El Nino, are graphically represented in Figure 8, where distinct time periods of below average and above average rainfall patterns have been depicted. Right, if you have a look at the graph just briefly, remember here to your left you have got the scale which shows you rainfall from 0 to 150 millimeters per year, or 0 to negative 150 where there's no rain. And then horizontally here along this axis down here, we are looking at time from 1900 all the way through to the year 2000. So we've got time there depicted in decades, and we've got the bar charts showing you rainfall patterns, and then a trend line where they have basically shown you where there's above normal and below normal recorded levels of rainfall throughout time. All right. Now this graph, rainfall fluctuations in Africa over the period 1900 to 2000, basically shows you where we've had La Nina and then El Nino events, right? El Nino where things change, and La Nina where things are supposedly sort of normal and as we expect them to be. The El Nino and La Nina is something scientists are still trying to work out as to why it actually occurs. As I said briefly in our explanation earlier, it's related to the changing of sea surface temperatures, and that affects wind because pressure belts are changed and slightly altered, and then the wind starts to blow slightly less intensely as what it usually does from place to place, and then your rainfall patterns are thrown out of sync as well by being regionally sort of disaffected or put into other places. If we have a look at the next section, we're now starting to move on to the use of more visual stimuli in your understanding of geography and climate. Particularly, we're going to be talking about the interpretation of synoptic or weather maps. Synoptic charts, or what we mean by a weather map of South Africa, looking at specifically things like air movements and the interpretation of station models. Right, so these two important things here, air movements on the one hand, and then interpreting or deciphering weather information from a station model, is what we're going to focus on now. Synoptic charts, or what we call weather maps, are drawn 4 times a day at your Greenwich Meridian Time, GMT. We are 2 hours ahead in South Africa relative to London and Greenwich. Hence, we create a synoptic map at these times: 2 o'clock in the morning, 8 o'clock in the morning, 2 o'clock in the afternoon, and 8 p.m. or 2000 hours at night. This allows for weather stations throughout the world to collect the weather data, and at exactly the same time to collate that information or put it together. And then climatologists or meteorologists are then able to create a global picture of what the weather is looking like in terms of your traditional elements. So temperature, wind speed, wind direction, pressure, all of those things that we measure, humidity, all the weather elements that you learnt about in grade 10. Climate data is collected by land-based weather places, so that's places that are on land. We also get weather from islands like Marion and Gough Island, and then ships are a very important source of information. They also record the weather conditions, and we get them radioed through or emailed through from ships. We are then able to plot the weather conditions to the west, south and east of South Africa. That's the only sort of area that we're interested in depicting the weather on a synoptic chart for our purposes on. And the major information that can be used from a synoptic chart is as follows. First of all, we can look at isobars. Remember, isobars are defined as lines joining places of the same air pressure. This is used to determine wind direction, wind speeds or strength, your subsidence of air that is sinking, your uplift of air that is rising. We also look at our station models that measure, right, the present weather conditions. So how hot or how cold it is, how fast or how slow the wind is, how wet or dry the air is, etc. Lines of latitude and lines of longitude are used to show the position of these weather phenomena, where they actually are occurring, and we can observe the approaching cold fronts, warm fronts, and seldom reach South Africa, remember. So we're interested in where is the cold front, when will the air become cold, when are we going to get a cold snap, and how's the weather going to change in relation to that arrival of a cold front with your mid-latitude cyclone or tropical temperate depression. Extratropical depression, they call them. The interpretation of synoptic charts of South Africa with special reference to air movements and interpretation of our station models. Let's have a look at air movements first. The two main surface circulation patterns of winds are those of the high-pressure anticyclones that we spoke about in the last lesson, and also low-pressure cells, or what we call cyclones, which we'll look at in Figure 9 in a minute. These must be understood as to where winds come from and their nature or their character, right? This allows us to understand weather and weather conditions that are resulting from these wind patterns or movement of air. In Lesson 2, the previous lesson, we looked at pressure gradient force, Coriolis force, and how all of those work together to impact on, firstly, the wind's speed, and secondly, the wind's direction as it traveled. And remember, you might need to go back and just to recap some of those basic principles we spoke about with Ferrell's law and the effect of Coriolis force, which we covered in Lesson 2. The two forces mentioned determine the circular flow that the air has around your high pressure or your low pressure system, which we can see in Figure 9. Isobars spacing determines the wind's speed. Remember, isobars that are closer together, there's a higher pressure gradient, so faster wind, stronger wind, whereas isobars that are spread out or further apart gives us slower wind speeds or weaker winds. Closely spaced isobars indicate your strength of the wind being strong. Isobars that are further apart, gentler or weaker winds. And remember, air always moves from a high pressure to a low pressure as it blows. So here you can see in a picture or a visual format what I've just been explaining with words. Here to the left there's a high pressure. This is what we call an anticyclone. And in the southern hemisphere, anticyclones will spin anti-clockwise as they move, and the air is descending, and as it gets to the ground it diverges in all directions. Whereas a cyclone or a low pressure cell, as depicted over here, you can see in the southern hemisphere spins in a clockwise direction as that air, which is warm, happens to rise and spin in a clockwise fashion through the cyclonic activity of rising or uplift of air. You can see on this diagram we've depicted the three forces we spoke about: PGF, Coriolis force, and wind being the resultant airflow, as depicted by those black arrows. And remember some of the little tricks we taught you last time. With your back to the wind in the southern hemisphere, Coriolis force is a deflection to the left. So if you put your thumb up, warm air rising is going to spin, and if you cup your hand and starts moving it, warm air is going to go clockwise. But cold, heavy air, put your thumb down for a high pressure or an anticyclone, left arm, cold heavy air is going to sink or subside and spin anti-clockwise as it sinks downwards, and then the other hemisphere for America and the northern hemisphere is depicted with your right hand. Right, so let's have a look at station models in more detail. Right, we have quickly spoken about the different air masses and how air is going to be interpreted or looked at on a synoptic chart. Now let's look at what is a station model and what do station models do or show. It is important to know that a full station model is drawn with the weather observations in specific positions around the circle. We're going to look at that in a minute. So your temperature is put somewhere, your wind direction, your wind speed, all of those things have their place or their spot around a station model, and you need to learn some of those conventions because it's going to help you interpret or understand the weather conditions that you're trying to decipher. Station models on synoptic charts are too small, much too small, to show all the weather conditions or observations of weather at the time. On Figure 10, the usual station model symbols have been circled, or I will point them out to you. Clearly, one cannot just place the 6 circled observations anywhere around the circle. The one exception is wind, which can be put, obviously, it can come from any direction, so that is changeable or can be varied. The common symbols used on station models I'll show you in a table, which is Figure 11 in a minute. But these are the classic 6 elements of weather or points of information which need to be depicted. The first one over there circled in blue, that is your wind direction, and that can change. It can be drawn anywhere around this little dot, this little thing in the middle. Yeah, this, by the way, where this is called the station model. On the ground or on the ship or on the island itself where they did the measurement of the weather conditions, that is the place where the weather was observed or physically recorded, right? That's called the station model. Now we can see this, for example, is a northwesterly wind. You always name a wind where it comes from. That's a northwesterly wind there. But the other things of importance is this. Your tails on the little feather of the wind, or what we call the wind speed, that needs to be depicted. This number over here, which is known as your temperature, the air temperature at the time, needs to be put on top. Then any weather conditions, we'll look what these stars symbolize in a minute, but that snow has to be represented between that number and this next one I'm circling down here. And then the bottom number that you have is your dew point temperature. Now remember, dew point temperature is the temperature at which air has to cool down to so that moisture can change from a gas to a liquid or a solid state when you've got condensation or sublimation occurring in the air mass that you're talking about. All these other numbers that you see over here, we're not going to go into too much detail about what they are, but there's things like air pressure and other variables that are being depicted on that little symbolic representation of weather conditions over there. This is more important over here, your different standard symbols or conventions which we use to understand weather conditions. So you can learn this, and this you have to know off by heart. So a comma is drizzle, for example. An upside down triangle represents showers when it's raining. A normal dot, which is colored in, by the way, is rain. A snow is a symbol like a star. This, being a triangle the right way up, represents when it's going to be hailing. And then there's your symbol for a thunderstorm, right? That looks like a T with a lightning bolt. Thunderstorm with lightning and heavy rain. And then you've got other symbols here, heavy rain, sleet, a snowstorm, right, where there's obviously showers and snow happening at the same time. Misty weather is depicted by 2 lines, and 3 lines is mist. These will all be represented between the 2 numbers that we saw over here, and between those 2 numbers there, whatever symbol they put here will tell you the precipitation that is occurring at that time. Then the second column here, or the third column rather, is a symbol for our next variable, which is cloud cover. If there's no clouds in the sky, then it'll be left open or unshaded. It's blank. 1 octa, remember we measure cloud cover in eighths? Is it 1/8, 2/8, 3/8, 4/8? In terms of proportion of cloud cover to clear sky, you can look at it as a proportion of 8. And using octaves, we can then measure the cloud cover on that particular day, or at that specific time, rather. And remember, I gave you those times earlier, 6 o'clock, 8 o'clock, 2 o'clock, and then 8 p.m. again. 2 octaves, there's quite a bit of cloud in the sky. 3 octaves, 4 octaves, and then we start talking about partly cloudy to very cloudy. And then this is when it is completely overcast, 8/8. There's no sky to be seen. It's just cloud cover above your head, so it's overcast conditions. If it's dark or it's not cloud cover is not visible or not clearly seen, they will symbolize it with this strange symbol of an X in that circle to show you that that's the scenario over there. Right, the last 2 columns over here represent our wind speed, and there you can see the symbols for wind speed in this column going down over here. If it is calm, then obviously there's going to be a circle within a circle. There's no air movement at the time, but wind can vacillate from 1 to very fast flowing air, so they've got a scale here on the right here. If it's a 1 to 2 knot wind, and remember a knot is about 1,8 kilometers per hour, we've got a 5 knot wind where it's a little feather, a 10 knot wind where it's a longer feather, and then obviously they can work in scales over here. There you can see a small one and a big one is 15 knots, for example. 2 big ones is 20 knots, etc. If it's going to be very fast moving air, in other words, above 50 knots or more, this is a gale, not quite a gale force wind, but a very fast gushing wind now at this stage, then an upside down triangle shaded in, or what looks like an aircraft's tail feather, is going to be depicted on the wind line. Remember, the line indicates the direction of the wind, and then the little marking on the edge of the line depicts your wind movement in terms of speed or velocity. Right, so we've looked at air movement, and we've looked at how you can decipher a station model. Let's look at the last aspect of interpreting synoptic charts at this point in your climate careers, and that is looking at fronts. So we're still dealing with the interpretation of synoptic charts of South Africa with special reference to air movements and interpreting station models, but we're looking now at fronts and how you look at a front and decipher what it says or means. Remember, fronts commonly affect South Africa in winter. We only have cold fronts in winter, and are present on the South African synoptic charts in summer, but they're much further to the south, and we don't experience them. That's why we don't talk about them too much. We really hear about them on the weather and talk about them in a lot of detail when we're experiencing that cold, nasty winter air, and because it's a winter phenomenon, we notice them more. But they do occur in summer, right? Warm fronts seldom pass over South Africa, right, if at all, and cold fronts pass over South Africa, leaving very cold but sunny days behind as they go into the interior of the country. And you know, you can hear people talking about a cold front approaching because they see cirrus clouds in the sky and all those old wives' tales about how you can predict the weather by looking up into the sky. But cold fronts basically bring very cold, nasty, cold winter air. The fronts approach the country from the west, and they are responsible for the winter rainfall that we record in Cape, or in the Cape region. And here you can see a diagrammatic representation of a front, or a cold front specifically. Ahead of the cold front there's usually warmer, moist air, and remember, this whole thing is traveling in that direction. It's a mid-latitude cyclone which is bringing cold air from the poles and squeezing up the warm subtropical air from further north up into the air. But you're going to learn about mid-latitude cyclones or temperate cyclones, extratropical cyclones. They go by various names next year in grade 12 or in matric. Essentially, this cold, heavy air that's advancing like this here is behind a front, and this is the front here that I'm showing you. From the upper atmosphere, or the sort of upper reaches of the tropopause, down up onto the surface of the Earth. This is how they reach, like that. And then what you will see them as represented on a synoptic chart is a line, remember, with little teeth on it, which are shaded in. Now these little teeth A colleague of mine calls them shark teeth. Remember, when you get cold, your teeth chatter. So when you see these little teeth, you know that this is cold air, and they're represented on synoptic charts like that little shaded in triangle. All right, notice these triangle features on the Earth's surface that are used on your synoptic charts show the position of that cold front as it is blowing towards South Africa from the west as it moves with the westerly winds blowing towards the subcontinent of South Africa. All right. We're now going to take an ad break, and when we get back after the ad break, we are going to start looking at some typical exam questions that you're likely to encounter in this section of the exam, or your climatology section. So after the break, come back ready to do some hard work. Welcome back. I hope you're ready for some climatology questions now. Just before we go into your typical types of questions that you can encounter, a quick recap of what we were discussing before the break. Here you can see a synoptic chart, or an annotated synoptic chart. Remember, on most synoptic charts, what you need to do is spend a bit of time before you even read the questions or start the exercise, looking at the information that is depicted on the synoptic weather map for you, and start thinking about some of that visual data or information being given to you. The first thing is the date and the time. That's very significant because that tells you the time at which the synoptic chart represents in the day for the weather conditions. So this is a 6 o'clock in the morning scenario. And then we can see here that it's the 9th of May, right? We are into winter now already. We've gone past autumn and we're heading towards winter. So the fact that it's the May month shows you that this is a winter type synoptic chart. Then we've got other information, all right? Isobars, lines joining places of the same air pressure over here. So this is a high pressure, and then you can see other things like low pressures. There's a mid-latitude cyclone or a cold front we'll talk about in a minute, those sorts of things over there. Do not confuse these curvy lines for the coastline of the sub-Saharan African region and South Africa. I'm highlighting the coastline now to differentiate for you from the curly or curvy lines what is an isobar and what is a coastline. So don't confuse that for the isobars. That's a very important point. Then we've got high pressure systems, like I said, low pressure systems depicted on maps. And remember, this we spoke about in the last lesson. When you go in towards the center of a low pressure, those numbers will be less than 1,013 and will be getting less. Whereas when you go in towards the center of a high pressure or an anticyclone, those numbers are going to increase in value, and they're going to be more than 1,013 hectopascals to indicate a high pressure area. Right, then we've got typical things like a station model. In this case, this is a ship over the sea, but you can get islands, right? Gough Island and Marion Island are also depicted on your synoptic charts. Here's Gough Island over there, right? And Marion Island is somewhere over here to the sort of southwest of South Africa. I've just circled those two down over here. Gough Island and Marion Island are places where we have scientists doing research and collecting weather and climate data on a yearly basis. The last thing is the lines of latitude and longitude. These are used to help us see the position of certain station models or weather phenomenon like a ridge or a cutoff low or a trough of low pressure, all those different climatic terminology that we speak about. This is your lines of latitude, these flat lines that run like that, and then your lines of longitude, the ones that are running down, right, show our position relative to the Greenwich meridian. Remember, South Africa is south and east in the world, and so our positionality is important to understand on synoptic weather maps as well. Right, we will encounter a synoptic weather map in some of our questions that we're going to have a look at, but let's kick off with the first question of our example questions over there. Question number 1. It says, refer to the map below, figure 1A, showing Africa's climate regions and the climate graphs that match many of the climatic regions. Figures B to K. This is all in your notes that you get there, so you can follow along with me if you like, but it's all going to be on screen as well as I explain. Answer the questions that follow. Right, remember, in any test or exam scenario, you spend a bit of time looking at your visual information and deciphering the data or what they're trying to show you. Don't just go in there and start answering the questions when you haven't looked at the resource materials that they've given to you to engage with, and you must spend time doing a little bit of interpretation and thinking before you start answering. Right, so this is a map of Africa showing the various climatic regions. We can see that from the label to the figure beneath, figure 1. And this is familiar because we've seen it in our notes when I was doing the explanation earlier. These are the climatic regions or zones of Africa, the 6 that we spoke about earlier: Equatorial, Humid Tropical, Tropical, Sahalian or semi-desert, desert or Mediterranean. And here alongside we've got just a summary there of desert conditions, we've got a summary of the Equatorial, and we've got the Humid Tropical, the Sahalian, Mediterranean and tropical regions, all defined in terms of their latitudinal position, their typical weather conditions, their rainfall patterns, whether or not it's continental versus maritime in effect, etc. And also on the graph we've got some ocean currents depicted, 1, 2, 3, 4, 5. Remember, we've got the Somali, warm Somali, the warm Agulhas, which becomes the warm Mozambican, the cold Benguela, and then the cold Canary current there on the northern western side of Africa on the top there. Right, so, and then we've got a map of Africa with a political map of Africa with all the countries as well as their capital cities depicted in this very nicely color-coded political map of Africa. Right, so let's have a look at some of those graphs first. It says you must refer to the map and the graphs to answer these questions that follow, but let's just look at the graph quickly in more detail. Here you can see this is graph B, that's graph C, etc. We'll look at all of them in turn. But this graph, the first one, is Ouagadougou, a place in Burkina Faso, very small, interesting country in Africa. And what they're showing on the graph are 2 variables. Temperature on the one hand, in degrees Celsius, and that's the line graph, which I'm going to try and just trace over for you over there. And then on the other vertical axis, they are representing rainfall in millimeters, right, which is depicted as the bars, the green bar charts. And along the horizontal here, we show time through months of the year from January through to December, 12 months in a year. Right, if we have a just look at those very quickly, we've got Khartoum, Sudan as the second graph, graph C. We've got this place in Cameroon, graph D. Then Chad, graph E. South Africa, Cape Town, F. And Durban, G. And then Algiers in Algeria is H. And we've got Kisangani in Democratic Republic of Congo as I. J is Livingstone in Zambia. And I think we've still got one more. No, that's it. That's the graphs from B to J. Okay. Now, if we have a look here at the first question, right, we've looked at all those graphs in more detail now. Let's see what they want us to do. The first thing they want us to answer here is, what characteristics do we use to differentiate between one climate zone and another for 2 marks? Now, remember, if you've done your studying and you've learnt the 2 elements of weather or the variables we're talking about here, which differentiates one place from another in terms of climate, is temperature on the one hand, how hot or how cold the air is, and we measure that in degrees Celsius. And also rainfall patterns can be similar or dissimilar in places, and we measure that in millimeters using a rain gauge. So there, for 2 marks, you've said temperature 1 mark, rainfall 1 mark. Question 2. Africa is the only continent that can be regarded as a mirror image of each hemisphere. That's a statement. With regards to climate zones, provide or disprove this statement. Can you see it was in inverted commas there? So they're basically saying Africa is more or less the same to the north and to the south of the equator in terms of climate zones or climate regions. Is this true or false? Right or wrong? Prove or disprove the statement. And because we are asking you a 2 times 2 question, it means you're going to give us an answer and elaborate or substantiate or justify or explain or give reason. Okay. So for 4 marks here, you need to say that this is a true statement. Africa is indeed a mirror image to the north and the south of the equator when it comes to climate zones. And you can go back to some of your evidence over here if you have a look at the physical map yourself. Right. Here is the equator, more or less, give or take a few millimeters, as I'm just roughly sketching it over here. To the north and to the south, can you see there, we've got the similar color patterns. Those browns, those greens, those grays, those orangey browns are the same in both hemispheres in latitudinal sort of extent. So at the same sort of latitudes to the north and the same sort of latitudes to the south of the equator, you've got the same sort of color zones or color coding happening there. So it is in fact a true statement. Right. And we can say there in our reasons now that latitudinally, climate zones, push the wrong button over here, are similar to the north and south of the equator. Okay, for example, we can give an example here to earn our marks. 32 degrees north and 32 degrees south of the equator. Africa, capital A, in each hemisphere has a, now let's go and look, what type of climate? Look at your color coding there on your map, right? There and there, those two yellow colors, what were they? It's desert, semi-arid sort of region, right? Well, semi-arid is the Sahalian region, but there it's quite hot and quite dry. So we can just say there, then, for the last little bit of our rationale or explanation, has a hot, dry climate. Okay, now how are you going to get all your marks here in this answer? Let's have a look at that with you very quickly, and we'll use a nice orange color to show the mark allocation that your teacher is probably going to do. Right, it's a true statement because you've thought about proving or disproving that statement. So that was the first bit of work you had to do, 2 marks. And then here's your reason. Latitudinally, climate zones are similar to the north and south of the equator. For example, 32 degrees and north and south of the equator of Africa in each hemisphere is very hot and dry as a climate region. Okay, 4 marks, 2 times 2 gives you 4. Remember, in geography, we are rewarding you for thinking as well as giving us the answer. That is why we're doubling up those marks, and it's easy to earn high marks if you've done your studying and if you know your work. So make sure you learn and revise well. Right, let's have a look at the next question, question 1.3. It says, refer to climatic graphs, figures B, C, D, E, F, all the way through to K. Match any 6 of the climate graphs to the correct climatic region. All right, so let's see, B, C, D, E, F, G. We only have to do 6, remember, 1, 2, 3, 4, 5, 6. I'm going to do up to G, and we have to say what climatic region do they represent. All right, so if we go back to the tables, our first one is Burkina Faso, which is Ouagadougou, right, that little city or town. And if we look at that other map, which is also going to help us to do this, let's first locate where is Burkina Faso. Right, so if you have a look here, we've located Burkina Faso. It's that yellow country over there, with Ouagadougou being that dot or that little spatial entity over there. Now, there's where we are latitudinally. Remember, this sort of is the equator dividing, the equator runs here through Gabon and those sorts of places across South Africa, Africa rather, all the way through to the Horn of Africa, that side. And we are north of the equator. Our latitudinal extent there is sort of subtropical still, right? Not quite sure if the Tropic of Cancer runs through this country. But if we have a look at some of the information going to this map, right, we look there, we compare the 2 maps where we are, right? This is the sort of area that we highlighted on that first map where we've got Burkina Faso. So sections of it sits in desert, sections of it sits, Sahalian, the grey area, sections of it sits in this sort of region over here, where it is a transition zone between monsoonal and desert-like conditions. The ITCZ is moving north. Summer rainfall is being experienced. It's mainly a continental type of climate. And some parts of it sit in that like green zone, which is tropical savanna. So here's all the detail there, where we're talking about the latitudinal extent being 15 to 20 north-south. The Equator Sub-tropical high pressure is dominant over the region in the winter months. Summer rainfall, but it is prone to a lot of drought and a lot of tornado activity. There's large temperature variations in this type of a climate zone or region. Right, so we're going to look at that, and we're going to say, if you look carefully, you can sort of see some of the borders or shading of the borders for those sorts of places. It's predominantly in the green zone, so we are going to label it as our tropical climate zone, or what's also known in some textbooks as your savanna area or savanna region. So we write that down next to B is the label there. That is a tropical climate or a savanna zone. Right, then C, let's just do another one there. You can see what this question is asking you to do, a little bit of identification. But you should also have interpreted this graph to see when do they get most of their rainfall throughout the year, and what are the temperature sort of ranges like from when it's hottest to when it's coldest, and then that'll help you decipher some of the information that you need to do as well. So let's have a look at the next one, Sudan or Khartoum. Again, we have to find it on the map first. Sudan is a very large country, so this should be quite easy for you to do. Right, and if you have a look at your map, here is Sudan. Let me just use the right color here so that we can do this and you be able to see it. There is Sudan. Right, so Sudan's latitudinal position we get a sense of from looking at this map. Then if we go up or down rather to those graphs, let's have just look at some of their climate data. It rains mostly in August, and when does it get the hottest in the year? Right, sort of from June, end of May up to June, that's the hottest temperature on the line graph, but the most rain is recorded in August, so this is its sort of hot and wet season, right? Summer rainfall and summer for them is June, July, and a little bit of August. And we can also look at the amount of rainfall they get there by looking at the value of the bars and how much is depicted, etc., etc. But if we go back to our graph and we have a look at our map with our colors rather, not graph, map, we can see Sudan here, this big sort of region over here, and it falls in a host or a range of climatic zones. But if we just take the sort of geographical middle or area over there, it falls again into this tropical savanna zone, and we can put that down as our answer for question number 1.3 C. Right, we're going to label that as well, tropical savanna, etc. Right, to save time, I'm going to move on and do some other questions so that we don't spend too much time on this one. But there are 6 labels here, and you've identified them correctly. You're going to get 2 marks per label and 12 marks for this question entirely. If we have a look at the next one, question 1.4, identify, there's your task word, your key question word. Identify and name the 5 ocean currents that wash the shores of Africa. Right, we can go back and simply do this by looking at our map, and there they are. We've got number 1, and you've done your studying now. That's the cold Canary current. Number 2, this one is the cold Benguela, and we can name them as we go, 3, 4, and 5. So if we go and we fill it in on our answer sheet, what is each of those respectively? We've got, first of all, the cold Canary ocean current. Then we've got another cold one called the cold Benguela that runs up on the west coast of South Africa. All right, then we've got a warm water body over there at 3 and at 4. All Right, so we've got the warm. Let's just go and look back at our diagram over here. Quite a bit of paging forwards and backwards for you in your geography exam, I'm afraid. And you have to now look at, we've labeled that one, the cold Canary. This is the cold Benguela. So number 3, this one that runs past the east coast of South Africa over there, right, is the Agulhas. And when we write that up, it's not as warm as the other water of those other currents over there. So we can actually make a note of that over here and just write that it is cool Agulhas. Then we've got the warm Mozambican, which runs further north, but it's also still, the water's coming from the equator, so it's hot water or warm water. And then finally the very warm Somali current, which runs there by the Horn of Africa, that brings warm water from the equator as well. Question 1.5, in which season does a Mediterranean climate zone receive its rainfall? Now the word Mediterranean there and rainfall should immediately tell you that we are looking for at a winter rainfall type of climate. So you get 2 marks for question 1.5. Right, now we move on to a new question. Question number 2. It says, refer to figure 2a and 2b that shows El Nino conditions and La Nina, also known as normal conditions by some scientists. And here you've got a very nice graphic, beautiful picture showing you from the tropopause all the way down to sea surface, right, that little vertical continuum over there. We've got a 3-dimensional perspective here of what air is doing laterally and horizontally as well as vertically. And here you can see, if you just decipher your diagram a little bit, remember we spend a bit of time looking at the information first before we just jump in and answer. So let's read the caption. It says, the oscillation between El Nino and La Nina conditions in the equatorial Eastern Pacific Ocean, that's where we are in the world, is called the ENSO, El Nino Southern Oscillation. It's an acronym for that, ENSO, and you can see where this figure was sourced from. But on this map we can see here is South America, and here is Australia. So now we know where we are in the world. And the bottom map is the same. 2B, Australia is to the left and South America is there to the right. But they've labeled for us that there's a desert over there. And they've also shown us here in what's called the Walker circulation how the air is blowing on the surface as trade winds over there. This little section over there are these trade winds that are blowing there. They're known as the southeast trades that normally do that sort of thing. But in a La Nina scenario, notice how that is all much stronger, because in El Nino the converse is happening. Those winds are weaker. They're not causing as much upwelling along the coast here for the Peruvian fish industry. All of those things you read in your textbook, how El Nino has an effect on the society, the economy, and all of that stuff, as well as physical effect on climate or weather conditions. And now let's have a look at some of the questions they're asking us in relation to how this is different to that from one scenario to another. Remember, El Nino is when the weather conditions are abnormal, and La Nina is when they're considered normal or as should be. Right, so the first question says, 2.1. Identify the surface pressure at A, B, and C. In each case, give a reason for your answer. Right, so what is it like at A, B, and C? High pressures or low pressures? And why are we saying high or low? That's the reason. We're going to get 6 marks out of this question. And so let's go back and have a look at our diagram. So what are the conditions here like at each of these places, right? A, B, C, and those are the 3 they want us to do. Let's just clean this up a bit so I can show you what we're talking about over here. Right, so there is A. What is the air pressure like over there? Here's B. What's the air pressure like over there? And C. What's the air pressure like over there? Right, now you should immediately be able to see from the diagram above all of those letters. At A, the air is hot and rising, so that's a low pressure. Whereas at B, which is the one side of the convective Walker circulation cell, the air is sinking because it's cold and heavy, so that's a high pressure. And air always blows from a high pressure to a low pressure. There's the surface winds, which have been weakened. This is an El Nino scenario. Whereas here at C, look above, the air is cold and dry and sinking, and it's creating hot, arid conditions over here for these poor people. They're having like a drought scenario during El Nino times. Same can happen for us in South Africa. So there we've got those three that we now need to go and label. So A was low, B high, and C high as well. Let's go and label those on our answers. We have identified each of those in turn, and now we're going to write them down. A was a low pressure area, hot air rising. B was an area or a zone of higher air pressure or high pressure. Cold air was subsiding or sinking. And C was also an area of high pressure there over Australia, because they had that cold, heavy air sinking or subsiding as well. We prefer to use this word subsiding rather than sinking in climatology, so just remember that and use the correct terminology to get the right marks. Question 2.2. The movements of air at D and at E have names. What are these names? So let's go back to D and back to E. Right, D over here, what do we call it when this air subsides like that? And E, what do we call it when air rises like that? Right, at E, where the air is rising, remember we call that an updraft or convection, whereas at D, where air is sinking or subsiding, we call that a downdraft or subsidence. Right, so we can just go and write that here in our answer. D is convection, which leads to an updraft, whereas E is subsidence, or air that subsides, which leads to a downdraft. D-R-A-U, not A-U-G-T, that's the other type of draft, eh? Draft here is movement of air, spelled like that. So we're getting 2 marks here for that and our explanation, and then 2 marks here for that and our explanation. There's 4 marks being earned here for question 2.2. Question 2.3, identify, right, there's our key word, name, and give the name of, identify the areas where drought conditions or that have drought conditions during an El Nino event by using figure 2.A. We're looking at 1 times 2 mark question, so you need to give a region or an area and correctly have identified it, so then you're going to get your 2 marks over there. And if we have a look back at this diagram here, figure 2.A is the one they want us to use. This is the region here. We are talking about drought conditions related to this subsidence of cold, heavy air that is sinking, warming up adiabatically and creating hot or dry conditions on the ground. And this is the sort of places that are going to be having this drought condition. So we're talking about Indonesia and those sorts of countries there in that part of the world. So you can go, oh, I'm going the wrong direction. You go back to your answer sheet and you write down there for question 2.3. Right, we get us some space here. We are looking at places like Indonesia and countries in the Far East. Right, for 2 marks over there. Australia can also suffer at the hands of El Nino at some point. So these sorts of things have been said to happen in our climatic history or past. Right, in the next question, we're going on to number 2.4 now. It says, from your answer, now they're talking about previously 2.3, explain the weather that would be experienced during the drought conditions brought about by El Nino conditions. This is a 2 times 2, a 4-mark question. We need to explain, there's our question or our task word, explain the weather conditions that could be or would be experienced during the drought conditions brought about by El Nino, right? And what is weather? Remember, what sorts of things are we looking at here in terms of elements or variables that we're going to be discussing? So for 2 times 2, you can say there that because of El Nino, or El Nino is going to cause or accentuate drought conditions, which will lead to higher temperatures. And they can have things like heat waves and all sorts of other problems associated with higher temperatures, and lower rainfall or less rainfall, in fact, and that could lead to all sorts of problems like water shortages and failures of crops, livestock dying of thirst. All those sorts of problems can ensue if we have drought conditions being reinforced or caused as a result of El Nino, making things even worse than what they are. Then here's your big question now. Question 2.5, 6 times 2 marks, 12 marks to write your paragraph. Right, remember, we're always going to have these more difficult questions towards the end of the question, and they're going to be for more marks, because this is where we want you to think and apply your minds and give us some of your insight from all your studying and your understanding of geography. Write a paragraph. Now remember, paragraph is usually at least 5 to 10 lines about the effect that El Nino, there's the first thing we have to do. What effect does El Nino event would have on Southern Africa, right? How will it affect Southern Africa, places like Botswana, Zimbabwe, South Africa, all of those countries that we are bordered and neighbored by? In your answer, number 2, this is the second part of the question, in your answer, refer to economic, that's the first thing, social, that's the second thing, and environmental effects or environmental problems that are going to be as a result of El Nino. So for 12 marks here, we need to talk about the effect El Nino has on South Africa by looking at specifically economic impacts, social impacts, and environmental impacts that it's going to cause. What are those issues or problems going to be? Right. So let's just try and keep a little bit of this question on the board so you can see while I'm writing the answer what we're talking about. Like that. Okay, that should give me enough space to write. Right, so for 6 times 2, 12 marks, first thing we're going to say is that El Nino will negatively affect, badly, right? It's going to have a horrible influence, the Southern African region by inducing or worsening already dry and hot conditions. Okay, what El Nino can do is it can basically cause drought to be more of a problem or make it even exacerbated. Economically, now we start with the first point over there. Economically, countries, and now we're talking about places in Southern Africa, remember, will suffer crop losses and even higher levels of employment, because remember, people are going to lose their jobs if the agricultural industry collapses, and they're going to be laid off or retrenched, because when the plants or the animals are dead, you don't need to employ those people to tend to them or look after them because they're gone. Right? Socially speaking, we can talk about issues like socially, these countries will suffer more homelessness. People will lose their jobs. They'll have to move to the cities. They'll have to go and try and find a job in the urban areas, and you can have all sorts of issues there. Countries will suffer more homelessness. There will be more malnutrition, and even hunger, right? And remember, we call those sorts of things that happen in the world where people are starving or don't have enough food, famine. So these are the sorts of things that can ensue or happen as a result of that. And then remember, we're looking at environmental effects as well. So let's talk a little bit about the environment now in the last part of our paragraph. Environmental effects would include water shortages and negative impacts on the ecosystems or ecology as a result of too little or no rain. So basically, people are going to suffer. The environment, animals, everyone is going to be negatively affected by El Nino. And this is what we're looking for here in our answer, right? That it's a negative effect. 2 marks. The Southern African region will be induced or exacerbated by the worsening effect of dry or hot conditions. Economically speaking, countries will suffer crop losses and even high levels of unemployment. 1, 2, 3, 4, 5, 6, 7, 8 marks now. Socially speaking, there's more homelessness because of people suffering, things like malnutrition and hunger or famine being a problem. Environmentally speaking, the effects are quite bad as well. Water shortages would be a negative impact on the ecosystems or the environment. This is as a result of too little or no sufficient rainfall patterns. So we're looking for 12 marks there, 6 points that you've elaborated upon or justified or reasoned through or explained nicely in more detail, and you can get 12 marks there for question 2.5. Account for the desert labeled on figure 2A. Right? Account means give a reason for or say why it is so. So let's go back to figure 2.A and have a look over there. And we're talking about this desert over here that's been circled in pink. I must have explained that previously when we were talking about this diagram. Why is there a desert there in that part of South America specifically? Remember, coming up along the west coast of South America here is a cold current called the Humboldt. Cold current from the South Pole. And remember, cold air doesn't cause high levels of evaporation, so it's going to basically be a very moisture poor environment, and that's why deserts can exist in that context. So for question 2.6 here, we're saying the reason we've got a desert there is because the cold Humboldt ocean current, less evaporation occurs along the west coast of South America, creating desert-like conditions. Right, so it's very hot and arid there and dry. Okay, 2 marks. Without further ado, thank you for joining us for climatology and today's lesson on Africa's climate regions. All the best for your exams. Study hard and work well, and do geography.